Hi, everyone, and welcome back. It's Kira Garfolo with Greenville Tech's Math 109. Today, we're going to wrap up Chapter 3 by talking about Section 3.4, which is quadratic and power models. So if you remember in Chapter 2, we had some data points and we were fitting a linear model to them. Remember that it was only appropriate if our data had that straight line appearance or if those first differences were relatively constant. In reality, that's not overly common. So sometimes we don't have that straight line, and using a linear model wouldn't really be appropriate because it wouldn't really be a meaningful model. It would mislead us potentially. But that doesn't mean that everything is lost. Sometimes we can fit a different type of model, such as a quadratic or a power function, like what we're going to talk about today. There are even more beyond the scope of our class that will fit pretty much any type of data. And using one of these models, we can get a much better fit and a much better model. Let's start with an example. Let's say that we have these 3 points, -1,9, 2,6, and 3,13. We want to find the equation of the parabola that goes through all 3 points. So remember that a parabola is by definition from a quadratic. If we plot these points, we can see that there's a parabola that goes through them. Since we're dealing with a quadratic, remember that quadratics are often presented in the form y equals ax squared plus bx plus c. So we need to find values of a, b, and c to give us this equation. So on the next slide, what we're going to do is plug each value of x and each value of y from each point into the equation. So we're going to do that once per point. So what we're going to end up with is a system of 3 equations, each equation representing 1 point, and then we'll solve for a, b, and c. So remember, everything that we learned in Chapter 2 and everything we learned with matrices in Chapter 7 can certainly help us with these solutions here. So plugging in these points, we would get -1,9 is going to give us a times -1 squared plus b times -1 plus c. Remember, these are just plugging in that x value, equals 9, which is our y value, which if we work that out and simplify, it'll give us a minus b plus c equals 9. If we do the same thing for 2,6 and 3,13, we're going to get these 2 equations also. And so now we have a system of equations we can solve. Remember, you can always pause the video to work this out and make sure that you can follow along. So now you're going to use what you learned in Chapter 7 to solve this system with a calculator. I encourage you to use an augmented matrix approach and solve it using RREF, that reduced row echelon format. If you use that final column that you get is going to be your answers for A, B, and C, respectively. When you do this, you should get A equals 2, B equals -3, and C equals 4. Make sure you take a few moments and that you can repeat these solutions. When we plug A, B, and C back into our quadratic formula, we have y equals 2x squared minus 3x plus 4. Again, A is 2, B is -3, and C is 4. That is where all of that is coming from. Now, in our earlier example that we just did, our points fell perfectly on the line. So the parabola went directly through all 3 points. As we saw with linear models, though, that's not always true, right? If we have real data tends to be messy, and they're not going to all fall perfectly where predicted every time. Just like we made linear models that were approximate, we can also approximate quadratic models. Essentially, we're still finding the line of best fit, but now we have parabolic shaped data. So we're using a quadratic instead of a linear model. We are definitely going to let our calculators do the work for us here. These can be done by hand, but it's not simple and it takes a lot of time. So instead, we're going to let our calculators do the work just like we did for linear regression. And we're going to see how here in a moment. Let's work through an example to see the steps necessary in the calculator. We want to find a quadratic function of best fit for the data below. In this table, X is going to be the number of years after 2000, and Y is going to be the value of the US mobile internet advertising market in billions of dollars. So as you suspect, since 2000, the internet advertising is going up, but we're going to see that it's actually going up at a quadratic rate. So here's our data. And just as a side note, in our textbook and elsewhere, it just gives the year and it gives Y. Make sure that you're careful here with X. It's not 2006, it's the number of years after 2000. So X is 6, X is 7, 8, and so on. So in our calculator, we're going to enter the scatter plot in stat edit, just like before. You'll have L1 and L2. Then we're going to press stat and we're going to select quad reg. This is just like we did with linear regression, except now we're doing quadratic regression. And the model is going to output A, B, and C, and we'll just plug those in for AX squared plus BX plus C equals Y. Now, if you wanted to show this on a graph, just like before with the linear models, you can store the results from your regression equation as that vars Y1, following the same procedures that you saw in section 2.2. So let's take a look here. I am going to first enter my data. So I have 6, 7, 8, 9, 10, 11, and 12. And then for my Y values, I have 0.045, 0.114, 0.273, 0.409, 0.545, 0.791, and 1.023. Calculator catch up. This emulator is great, except it's not quite as fast as what we would see on a real calculator. Now, once that data is there, we can say stat, scroll over to this calc, and we're going to scroll down, not over. We are going to scroll down to quad reg. That is quadratic regression. And we're going to press enter. As long as X is in your first column and Y is in your second column, you leave these alone. We don't do anything for frequency list. Now, I like, especially to look at it on a graph, to store our regression equation. This is just the exact same that we did when we were doing linear regression. You can store it under vars, scroll over to Y vars, it's a function, and it's Y1. And you press calculate. It's going to think for a second, and then it's going to give this output. So it's telling us that it's giving us AX squared plus BX plus C, where A is 0.01488, B is negative 0.105, and C is 0.1373. So we can plug those in and get our equation. Now, if we want to see this on the graph, we need to turn our scatter plot on. So we go to stat plot and we turn this graph on. Now I like to go to zoom. Remember that Y is saved as our model. Instead of looking at the standard, I'm just going to tell it to zoom stat here. And there it is. We can see our points here. And we see the quadratic model that goes straight through it. Going back over to the PowerPoint. Here are the steps in case you want to have them for quick reference instead of watching the video again. We're going to input our data, choose quadratic regression. This is our input. Remember, we use vars for this. And here's our output. So we see that this is Y equals 0.0149x squared minus 0.105x plus 0.137. So that 0.0149 is A, that negative 0.105 is B, and that 0.137 rounded is C. It's always a good idea to look at your graph because it'll show you that fit, right? You can get an idea for if it's a good fit or a bad fit. I encourage you to take a moment and make sure you can replicate these results. Again, you can pause the video as needed. Now, it's all fun and games to make a quadratic model, right? We can make it for really any data set, but is it actually appropriate to make a quadratic model? We can look at this similarly to the way that we looked at linear models. Remember when we had the linear models, we looked at the things called first differences. So as long as X was going up by uniform amounts, so 1 going up by 1, going up by 2, going up by 100, as long as it was uniform that way, we could look at first differences by finding the consecutive differences in Y values. Now, if those first differences were approximately constant, then linear models were appropriate. If they weren't, all we could say at that point was that, hey, a linear model isn't a good idea. For quadratics, where we have a degree of 2, a second difference is a better approach. So now we're going to still find our first differences, but then we're going to find the first differences of the first differences. Sounds redundant because it kind of is. But find your first differences and then use those to find the differences. Those will be your second differences. Let's look at an example because that was a lot of the word difference. So let's consider this data. We have different X values. We see the X is going up by 1 each time. And we have these different Y values. Our first differences are 49, 29.4, 9.8, and so on. We can see that those aren't anywhere really near constant, right? But our second differences will be these values, right? 29.4 minus 49 is going to give us negative 19.6. 9.8 minus 29.4 is going to give us negative 19.6. Negative 9.8 minus 9.8 is going to give us negative 19.6, and so on. So this is actually an exact quadratic fit because our second differences are identical. Remember that real data is messy, so identical would mean that those points all fall in the parabola, but more common in the real world is going to be that they're going to be roughly constant, but they're not going to be precisely constant. So you'll be doing a line of best fit and not just a line that goes through every single point. Now, I encourage you to pause this video for a moment. Use this data on the left-hand side table, use this X and this Y to create the quadratic equation to fit that data in the table. Again, give it a pause, do what we did a few slides ago, and find that quadratic equation. You should get the solution Y equals negative 9.8x squared plus 78.4x. Here, you're going to get a value of 0 for C, and so that's why we just leave it off. So far we've talked about linear, where we're talking about X as 1 degree, right? No, there's not going to be any exponent on X. It's just that straight line. And then we're going to talk about quadratics, where we had X squared as a component. But that's not always going to cover all of our data. So we can also talk about power functions. So if your data isn't linear and it's not quadratic, it very well may be a power function. Again, this would be great if all 3 of these would work, but really there are some that none of these work for, but hopefully that'll be limited on course. We can use what are called power functions. Again, we're going to let the calculator do all of the work for us in a power function. So in your calculator, it's going to be strikingly similar to what we've already done today and what we did in chapter 2. Enter your data into L1 and L2 just like before, and you're going to go to Stat, Calc, and instead of choosing linear regression or quadratic regression, now you're going to scroll all the way near the bottom and choose Power Reg or PWR Reg. The output is going to be very similar as before. Just pay attention to the format. Now you don't have any pluses or anything like that. You just have a formula of AX to the B. So it's going to give you A and it's going to give you B, and that is going to be the format of your answer. You'll plug the A in, you'll plug the B in. Let's look at an example. We want to find the power function that's the best fit for this data, where X is the number of years after 1950 and Y is the number of households in thousands that cohabit without marriage. I want you to pause here and give it a try because you've already worked through these using quadratics and linear. We're just changing the type of function. Just be very careful here. Remember the definition of X above. 1960 is not an X value of 1960, but rather 10 because it's 10 years after 1950. Pause the video, give yourself a moment to work this out, and then move forward. Okay, I'm going to work through it here in the calculator also. So I am going to edit my lists. And so 1960 is 10 years, 70 is 20, 80 is 30, 85 is 35, not 350. So we have 10, 20, 30, 35, 40, 45. And then we have, let's see, 52, 54, 57, 58, 60, 61, 62, and 63. And then for L2, we have 439, 523, 1589, 1983, 2856, 3668, 4898, 5080, 6209, 6214, 6768, 6715, 6928, and 7046. Be very careful inputting these. I made a typo last night and it took me a long time to figure out where the typo was. So always take the time and see. Okay, so now we'll press Stat. We'll scroll over to Calc. I'm going to actually hit the up button because it'll take me to the bottom faster. But Power Reg on the 84 is option A. Press Enter. We're going to do L1, L2. I'm not going to store these here. You can store them and graph them just the same as before. But I'm going to hit Calculate to get my equation. It's going to think for a second. And then we're going to see, it gives us the format AX to the B, where A is 5.105 and B is 1.731. So our equation here would be 5.105x to the 1.731 power. Going back over here to our PowerPoint, we can see our output here, again, here for your reference. Here's our data input. Here's where we choose, and here's our output. So our best model is y equals 5.105x to the 1.731. Now we can also compare a quadratic and power model, because if I didn't tell you which was the better one, you wouldn't necessarily know which was the better one. If we input the same data, or left the input in our calculator in our case, and we created a quadratic equation for it, again, you would just go into Stat and you choose quad reg instead of that, you would get the model y equals 2.100x squared minus 21.78x plus 313.992. Which of these models is better, and how do we tell? That's a pretty loaded question. And as a statistician, I think our book kind of short sells us on this, but I'm sure I'm biased because, again, I'm a statistician. So the better fit, according to our textbook, is to look at the graphs. So plot the points and see which line is the better fit, which one goes through or closest to more points, which one follows the trend overall better. In my advice, you can also consider, not individually consider, but also consider the R-squared value. Our textbook doesn't mention this, but I think it's an easy way to get a more concrete answer. R-squared is output automatically by our calculators as long as your diagnostics are on, which they should be. That's how you found that correlation coefficient in chapter 2. So remember right here in our output, it does it for power reg too. This R-squared value is an important measure of model fit. I'm not going to get into the specifics of what it means statistically, but it's between 0 and 1, and closer to 1 is better. So 0.995 is really good. It's very close to 1. So that's a pretty good fit. Let's look at our example. If we graphed it, we can see that the red is our quadratic and the black is our power model. It looks like the red is a better fit for our data. It captures that curve more than this black, not as curvy line for the power model. If we compare our R-squared, scrolling back, the R-squared for the power, or for the quadratic, is 0.996 roughly. If we go back to the solution for the power reg, the R-squared is 0.945. Be careful here, you're looking for R-squared, not just R. So the R-squared is 0.945. That is lower than 0.995. And so as confirmed by the graph, R-squared is higher. It's a better model fit as the quadratic instead of the power. So that's all we're going to talk about for section 3-4. But in conclusion, make sure that you let the calculator do your work for you. These are very difficult to do by hand, and they take a lot of time. So be comfortable with your calculator if you're not already, and let it do the work for you when it comes to regression. When you're trying to determine which model might be best, always take a look at the graph. Is it straight line? Is it curvy? How curvy is it? You can consider your first differences to determine if linear is more appropriate. Your second difference is to see if it may be quadratic. And then you can, if you're comparing models, look at the graph on top of the scatter plot. And you can also compare those R-squared. Remember, R-squared is what you're looking at, and closer to 1 is better. As with everything in this class, practice, practice, practice. Do your homework, do any assignments, do any quizzes, do extra work if you need to. Your textbook has so many examples available for you. Remember to use all of your resources in Blackboard, the departmental lecture notes, any videos, publisher information. And remember that the Math Center is available, and remember that my office hours are available. If you have any questions, you know how to reach me. Otherwise, have a great day, and I hope to see you next time.